Okay, so let's go ahead and get started. Today, we will be talking about extrema of functions on a given interval. And we might get to something called gradient descent. I don't know, but we'll see. So this topic is extremely important for data science majors. In fact, all of this chapter 3, is really important. And because there is no calculus book that I know of that is designed for data science majors, a lot of the, well, not a lot, I'll say a portion of the topics that we covered will not be in the textbook. So it'll be really important that you do watch the lectures to stay on track for what we'll be doing. So let's begin with the definition, as usual. Okay. So we're going to assume, so maybe let f be defined on an interval I containing some value c. Okay, so f is defined on some interval I, and I contains this value c, and we'll have two parts. So part one, f of c is the minimum or a minimum of f on I when f of c is less than or equal to f of x for all x in I. Okay, and then likewise, f of c is the maximum or a maximum of f on I when f of c is greater than or equal to f of x for all x in I. Okay. Now, say these values are called extrema values or extreme values. And extrema is the singular. Of the extremal values. Okay. So let's consider maybe, so let's say f of x equals to x squared plus 1 on a closed interval -1 to 2. So what does this look like? So this is the x squared function raised up by 1. So it looks something like So that would be the graph of this function. And this is considered over this closed interval here. Of course, the function continues and is defined everywhere, but we're only concerned about on this interval. So we can see that we have the minimum of the function is there and the maximum is right there. Right, so, what would the extreme values be? So f of 0 is a minimum, and f of 2 is a maximum. Okay. Now, if we consider the open interval, -1 to 2, and if I draw this picture again, it would look like this. So something like that. Right. So now it's still the case that f of 0 in this other case over here is a minimum on that interval, but there is no maximum. So notice that because the function is not evaluated there at the endpoints, there can be no maximum. There is no maximum value for this function on that open interval. So maximum and minimum values do not necessarily need to exist on an interval. Right? And this is the case where the maximum does not exist. However, if the function is continuous on a closed interval, then we can guarantee the existence of a maximum and a minimum. For example, this is a continuous function on that closed interval, and we see that it does have a minimum and a maximum. And I'll state that actually as a theorem. So this is referred to as the extreme value theorem. And it's precisely what I just said. So if f is a continuous function on the closed interval AB, then f has both a minimum and a maximum on that interval. Okay. So we're guaranteed that a minimum and maximum exists on this closed interval, provided the function is continuous. Okay. Okay, so that's when we're given an interval, but a lot of times we won't know the interval in question where a minimum and maximum value will exist. So that leads us to another definition. and this is a relative extrema. Okay. So part one, if there is an open interval containing C, on which, say, f of C is a maximum or minimum, then f of C is a relative maximum. Or relative minimum, respectively. Okay. So, for example, if that's our function, right, then right there, right there, right there. See, these values here would be relative extrema, right? Because there is some small interval around, for example, here, where that is a maximum on that interval. Or like maybe here, there is some small interval around A where that's a relative minimum. Okay. Okay, so let's look at an example here. Let's find relative minimum and maximum. Relative minimum or relative maximum for the function f of x equals to 9x squared minus 3 over x cubed. Okay. So in order to do this, observe that at these relative maximum and minimum, what's the value of the derivative? What's the slope of the tangent line at those points? What is it?
0.
0, right? So one way to find relative minimum and maximum is to calculate the derivative and then set the derivative equal to 0 and find out the values for x for which that is true. That'll tell you when the tangent line is flat like that, which will tell you that there is some small interval where you have a relative min and relative max. So for this function here, we're going to have to use that messy quotient rule, which I hate using, but I think that'll be the fastest way to do it here. Okay, so it's the derivative of the numerator times the denominator first, so that'll be 18x times x cubed. So 18x is the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. So that's just plugging into that quotient formula for the derivative. Okay, so if we simplify this, what do we get? We get 18x to the power 4. So then we have 3x squared. So I'm going to leave the 9 out for now. Then 3x squared times x squared is, what is that? 3x to the power 4 minus 9x squared all over x to the power 6. So then we have 18x to the power 4 minus 27 x to the power 4 plus 81 x squared. That looks correct. All over x to the power 6. So what is that? Minus 9x to the power 4 plus 81x squared over x to the power 6. Okay, so let's factor out that 9. What do we get? So we can factor out let's factor out 9 times x squared. And what are we left with? Minus x squared plus 9 all over x to the power 6, which is equal to, I'll factor out a negative just to make it look nicer. So negative 9 times x squared minus 9 all over x to the power 4. So a little bit of algebraic simplification just to get it where we want it to be in its factored most simple form. So now we just need to set that equal to 0. So f prime of x equals to 0 is the same thing as saying minus 9 So when is that equal to 0? Well, it's when the numerator is equal to 0, right? And you can already see that if x is 3 or negative 3, then that's going to be 0, right? So, so x is equal to plus and minus 3. Okay. So if we plug these values into the function f, we should get relative minimum and relative maximum. Okay, so because those values assign the derivative equal to 0, which is when the tangent line to the slope is going to be flat, which is in a sense finding the relative minimum or relative maximum. And I'll leave it to you to plug those in, but to just plug in positive 3 into that, plug in negative 3 into that, and those will be relative extrema. Okay. Now, sometimes this idea will not work though. If the function isn't differentiable at a relative extrema, then this technique is not going to work. So for example, if we were wishing to find relative extreme of the absolute value function, well, what does that look like? We know that x equals to 0 gives us a relative minimum for that function. In fact, it's what's called a global minimum, because it's globally minimum among all other points. But the derivative doesn't exist at 0, right? So we wouldn't be able to use this technique to find them in that case if it's not differentiable at that point. But what would we call that? Well, this is going to introduce another definition. Okay. So let f be defined on an open interval containing C. Okay. So then should say x equals to C maybe. So then C is a critical value of f if f prime of C does not exist, or f prime of C is equal to 0. So that's the definition of a critical value, or a critical number. Yeah, I think your textbook says critical number. And for example, right there, x equals to 0 for that function. Okay. So that leads me to a theorem. A very important theorem. If f has a relative min or a relative maximum at x equals to C, then C is a critical number of x. So this is good, right? So if the function is going to have a relative min or relative max, then at that point the derivative of the function is either 0 or the derivative doesn't exist. So this is a good criteria to guarantee that we have some information about the function at that point. Right? And because I don't think it's necessary to cover that proof today, I'm just going to go ahead and make another video giving the proof of this theorem. It's not difficult, but in order to really understand it, I need to spend some time. In order to really explain it, I need to spend some time on the details of the proof. Even the textbook kind of gives a hand-wavy type of proof, and I don't want to do that for you. Okay. So now that we know that relative min and relative max are critical values, right? We have, in a sense, a method for finding maximum and minimum values of a function over some closed interval. And I guess I'll give like those guidelines here. So finding the extrema of a continuous function f on the closed interval AB. And these guidelines follow because this theorem ensures that we have information about the relative min and relative max. So I guess step one would be first, find all critical numbers. For f on that interval. Which I almost forgot, because the function is continuous on a closed interval, we know that it attains a maximum and a minimum on that interval by a previous theorem. By this theorem, we know that those maximum and minimum are going to appear at the critical numbers of that continuous function. So part two evaluates f. Oh, not closed interval, by the way. So this is a closed interval, but you want to find the critical numbers on the open interval AB, and then evaluate f on the critical numbers in that closed interval. Your first two steps. Step three is to evaluate f at the endpoints of the closed interval AB. And what that basically means is that just evaluate f of A and f of B. So find the value of the function on those endpoints. And then part four is the simplest. The maximum of these values is the maximum. And the same for the minimum. Okay. So that's a simple guideline for doing this, for finding the maximum and minimum of a continuous function on a closed interval. So, for example, let's consider f of x equals to x squared minus 4x plus 5 on the closed interval -1 to 3. And we want to find the maximum and minimum of this function on that closed interval. By the extreme value theorem, we know that that function does have maximum and minimum on that closed interval. It's a continuous function, it's a polynomial. So because we know that, then we can go over here and say, let's apply these steps and find the minimum and maximum of that function. All right, so part one, we need to find the critical numbers on the open interval AB, or the open interval -1, 3 in this case. So then we just need to find the derivative. Okay, so that function actually exists everywhere in the open interval -1, 3, so there are no values for which the derivative doesn't exist. So then we set this equal to 0, and then we get that the only critical value we get is x is equal to 2. So that's the only critical value that we found. So now we need to evaluate the function at the critical value. What is that? 4 minus 8 plus 5. So what is that? 1? Okay. So then step 3, we're going to evaluate f at the endpoints, -1 and 3. So f of -1 is equal to 1 plus 4 plus 5. Okay, so that's 10. And then f at 3 is going to be 9 minus 12 plus 5. So what is that? So 3, 2, so 2. So we see that we don't even know what that function looks like just by kind of not thinking about it much. But we know at 3 it's up here like maybe at 10. And then, oh no, at -1 it's up here at like 10. At 3 it's at like 2. And then at 2 it's at 1. So I bet you this is a parabola, so it's going to look like that. And we see that here is probably that where the derivative is equal to 0. But then at the endpoints, that's the maximum, that's the minimum. So that'd be part 4, it's just to say that those are the max and min. Okay. So it's a pretty standard, easy thing to do, provided you're comfortable with derivatives. And these are continuous functions, so you can find the derivatives. You'll know when the derivative doesn't exist, so you can find the critical values, the critical numbers. Just evaluate the function at the critical numbers. Evaluate the function at the endpoints, and then take the max and min, and those will be the max and min of that continuous function on that closed interval. Okay, so I'm going to pause the video. So yeah, I actually think this is a good place to stop the first recording. And then in the next recording, I'm going to show you something related to machine learning and finding Extrema. All right, so that will be the next video.